a simple example of machine learning problem. This will be classification problem. Data on 114 individuals with thyroid disease. 61 patients with elevated levels of free hormone T4 and 53 patients with normal hormone levels. And for each patient, the following features are known. They are the feature X1, the heart rate, and X2, the logarithm of so-called SDNN, the logarithm of the standard deviation of the duration of the intervals between sinus contraction of the heart. It isn't important for us what does these features means exactly, but you have to understand that we have two features and they are numerical. X1 is heart rate is numerical and X2 is numerical too. And we want to predict the level of T4 given the heart rate and the logarithm of SDNN. Here are the picture. This axis corresponds to the logarithm of SDNN, and this axis corresponds to the heart. 50 beats per second, 60 beats per second, and so on. And the logarithm of SDNN. And each point corresponds to the individual, to a patient. Red points correspond to patients with high level of T4, and the blue points correspond to the low level of T4. And we want to predict the level of T4 given these points. And you can see that red points are near to the left upper corner of this diagram, and blue points are near to the right lower corner of the diagram. For example, you can find this line with equation 16 times logarithm of SDNN minus heart plus 50 is equal to 0. Now it's not important how I obtained this line. In fact, I used support vector machine algorithms, but it's not important. But intuitively, it's clear that this line, separates blue points from red points rather well. Yeah, rather well. The most blue points are under the line, and the most red points are above the line. And the training error is 23%. What does it mean? It means that 23% of all these points doesn't classified by this decision rule correctly. For example, this blue point will be classified as red one, this blue point will be classified as red one, and so on. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think 11 blue points, which will be classified as red points. But we have also a few red points, which will be classified as blue ones. This red point, this, and so on. All these points, which will be classified incorrectly, are so-called errors. And these errors here are 23%. And can we decrease the error? Can we decrease the error? I think it's clear that if we will use only some simple decision rules, like this line, straight line, it's clear that we cannot decrease the error substantially. Yeah, it's about 23%. But we can use other interesting border, other interesting decision rules, like this one. Yeah. Here we have used nearest neighborhood methods. And here the training error is 0. What is nearest neighborhood method? It is rather simple. For example, we want to classify a new point, say something here, yeah, this point. We have to find the closest point in training set. I guess this one. This point is red. So this new point will be classified as red one. If I get a point close to this one, for example, here, yeah, you can find the closest point in training set, this one. So this point will be classified as blue, and so on. Any question? No. Okay. But which methods this one or this one works better? This one or this one? What do you think? Please, you can use chat or answer question by voice.
Sir, I think first one works better.
Why?
Sir, because we can separate with line. So it's clear line that separates the two, red and blue. But in the second picture, we have lots of areas. So we cannot clearly separate this blue and red dots because we have a lot of areas.
Lot of various. But here we have error. But here the error is 0, yeah, and here the error is 23. What is better, 23 error or 0 error?
No, 0 is of course it's better.
Yeah, but this is only the train error, yeah, the train error. It's easy to imagine that if we try to classify new points here, this classifier will work better, yeah. For example, if we'll have a dot here or here, it's this high probability it will be it will be red. And if we have a point here or here or here, something here, there's a higher probability it will be blue. So this classifies better, of course. For example, any point here will be classified as a red point, but it is clear that
it's blue.
Is as blue point, but it's clear that it's likely it will be likely red. Yeah. Here we have the result of other methods, k nearest neighborhood methods. The difference from nearest neighborhood methods or one nearest neighborhood methods is that here we have k nearest neighborhoods. Here we have 15 nearest neighborhood methods. For example, we want to classify this point, this one. We have to find 15 k neighborhoods. 1, 2, 3, 4, 5, 6, 7. I don't know. Maybe these points will be 15 points will be neighborhoods. And determine the color of this new point by majority voting. Yeah. Among all these 15 points, the majority will be red points. So this point will be red too. And note that when k is large, we will obtain the border for these two regions similar to line, like here. Yep. Okay. And what does it mean? It means that a small error, what's the conclusion? A small error in the training set doesn't mean that we classify new samples well. And overfitting is a phenomenon when the decision function works well for samples in the training set, but often fails for new samples. So poorly predicts the response to new data. Here, for example, our algorithm, our methods works perfectly on the training set, yeah, but the thing it poorly will poorly predict the response to new data. There is another phenomenon, underfitting, when the decision functions show poor results on both the training set and new data. Let's imagine that here, for example, we will use the constant method. So all new objects will be classified as red points, All points will be classified as red points. It's clear that these methods, this decision function will show poor results on both the training set and new data. It's clear. So the error will be about 1/2, 50%. And the main cause of overfitting is using too complicated model with too complicated border. Yeah, with too complicated decision function. Here they have too complicated border, yeah, too complicated decision function. And here we will have the overfitting. Here we have a simpler decision function, simpler border between two classes. And this decision function will work better. Here, the same situation, the same. We will have a simple decision function, rather simple decision function, simple decision boundary, and we have no overfitting here. We have no overfitting here. And the main cause of underfitting is using too simple model. Too simple model. Here or here, the constant model is too simple, surely, too simple. So we will have for constant model underfitting here, underfitting. Any question? Okay, no question. Training and test sets. Usually we will use training and test sets. We train the model on a training set and test it on new objects, new samples, on a test set, new data. And the learning algorithm shouldn't see the test set during training. So, for example, 60% of all your data should be considered as a training set, and the rest should be considered as a test set. Okay. Any question here? No question. Let's consider other example, example 2. We have data concerning 72,000, more than 72,000 flats in Nizhny Novgorod, and it is required to predict the price to predict the price. This is a regression problem because the price is a numerical feature, numerical. We have 9 features here. The date when, I don't know, the date when this information about the flat, when the information about the flat appeared in the site, yeah. The second feature is latitude. It's numerical feature. Longitude is numerical feature. The type of property, new building or resale, yeah. So this is a binary feature. The number of floors, numerical. Discrete, but numerical. The number of floors in the house, yeah, in the building. The house is the type of the house, brick, panel, block, monolithic, wooden, and all these types of house, all these types of houses. And what kind of feature is this? This is, of course, categorical, yeah? Categorical feature. The number of rooms. The number of rooms is numerical discrete feature. The studio, 1 room flat, 2 rooms flat, and so on. And studio 0 corresponds to the studio, flat studio. The floor is the number of the floor in which the floor is. which the flat is, the area, the area, площадь is area in Russian, of course, and the price, yeah, it's clear. Always, all two features are numerical. This is so-called regression problem, and I guess you know one of methods to solve regression problem, so-called least square method or linear regression. You have points x1, y1, x2, 1, 2, and so on, xn, yn, and we want to find a linear function b0 plus b1 times x, such that the squared errors is minimum. Find b0 and b1 to minimize the so-called the residual sum of squares. The residual sum of squares is equal to the sum for all y, for all objects, for all points, from 1 to n, fxy minus yi. F of xy is this one, yeah? b0 plus b1 xy. b0 plus b1 xy minus yi squared. What is fxi minus yi? This is this distance between the point and the corresponding point on the line. Is the same xy here for this point and xy for this point, but other y. Here we have f of xy. So this point, all these points are on the line. Yeah. And our problem is to minimize this function. Have you considered this problem previously in your on the courses? Did you study this problem previously?
Sir, we studied in our probability class, but we forgot the formulas.
But I think you remember how to solve optimization problems. There is rather universal universal methods to solve many optimization problems. If you want to minimize or maximize function, what we should do, what we have to do, okay, what we must do, usually.
Sir, making the derivatives of it.
Yeah, and then?
And then taking logarithm.
Logarithm, why? Yes,
So,
first of all, we have to make the derivative, yeah, find the derivative, yes. And when?
When the second derivative is negative, then it is the maximum point. And
yes, but what for the first derivative? In the minimum or the maximum, the derivative is zero, yeah?
Yes.
So in our case, when we want to find the minimum for all b0, b1, we want to find the derivatives b0 and the derivatives on b2, and we want to assign it to 0 here and to 0 here. And after a simple transformation, we'll obtain the so-called the system of normal equations. Sorry for the Russian text here. I forgot to correct it. Okay, the system of normal equations. B0 times n plus B1 times the sum of all x's is equal to the sum of all y's. And this is the first equation. And the second one is this one. Okay. For our example, we can to approximate the price for the flat in Nizhny Novgorod, given only the area. Yeah, given only the area. For example, we want to approximate y given x. We want to find B0 and B1, where y is price, x is area. Price is the price is between 0,000 rubles to 10,000 rubles. So, for example, this one is 6 millions rubles, and this is the area in meters squared. Yeah, 50 meters, 100 meters squared, and so on. And you can see that all these points are have the trend to lie near the line. This equation you can find solving the system of normal equations here. You can find B0. It will be minus 119.53. And B1 is 64 times dot 89. But you can solve this problem also when you have 2 features or 3 features or more features, x1 and x2. You have a lot of points here. For example, this point, this coordinates x1, y, x2, y, and y. And we want to find B0, B1, B0, B0, B1, and B2, such that the squared sum of squared or squares residual sum of squares is in minimum. In this situation, also you can find the partial derivatives, the derivative of RSS B0, RSS B1, and B2, and you get the system of normal equations. This is like this one, and you can solve it. For our examples here, when we have B0, B1, B2, y is price, x1 area, and x2 is the number of rooms in the flat, you can find that B0 is this one, B1 is this one, and B2 is this one. Okay. The next big homework will be the first point here: install Anaconda and all necessary libraries. Please install it and try to play with it. Yeah. And next lecture we'll consider the Anaconda distributive more accurately, Jupyter notebook more accurately, and we'll code some machine learning algorithms. Any question?
No question.
No question. Good for you. Okay. Okay. Good luck. See you next week. And what about your homework with essay? Have you prepared your essays? Please send me using our portal, yeah? Okay, goodbye.
Thank you. Have a nice day.
Nice day.